Hello, geometry. So here we are continuing with our shortcuts for proving triangles are congruent. We're going to get two shortcuts today. The first one is going to be our side, side, side. If you know that the corresponding sides altogether of the two triangles are congruent, then we know the two triangles are congruent. So the way we would say that is if three corresponding sides of one triangle are congruent to the three corresponding sides of another. Actually, I didn't need the corresponding part twice. A little overkill. Then we know the two triangles are congruent. All right, so basically, like I said before, our shortcuts are always going to involve three pieces of information. In this case, it's all three. And so when you are referring to this in a proof, you can say the side, side, side theorem. Okay, so here we go. We have our proof. And again, if you really want to test yourself, turn off the video and try this proof on your own. So we're going to write down our givens in that first box and just get these out of the way. So we have those two segments congruent. KL, which is here, is congruent to NL. And we are given that KM is congruent to NM. These should all have little lines over them. Sorry about that. And the reason we're allowed to say that is because it was given. And for my students, you know how I like to, if this is a part of the triangle that we're looking for, I'm going to highlight it. So I've got two parts so far, and it takes three parts to prove that two triangles are congruent. So remember, there's two things that you can get right from a diagram that they will never mark up. And you're looking for either a shared side or a vertical angle. And we can see in this case, we have a shared side, that LM is congruent to LM. And it's kind of like ding, 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 ding. We have our three pieces of information. So what lets me say that is your reflexive. That's what gives that to me. And now I can just sort of copy what's up here. Triangle KLM is going to be congruent to triangle NLM. And now our reason is going to be the side, side, side theorem. Okay, because that's the three parts we have. We have three corresponding parts. Okay, now we're going to get into a shortcut, and this is a little difficult because we never did constructions in this distance learning environment, but for my students I sort of already told you what shortcuts work and which don't. And remember, ask backwards does not work. In other words, and actually AAA and ask backwards are the two that do not work of all our shortcuts. I'm going to attempt to kind of show you why. If I have, let me see, so this is angle, side, and a side. So if I have an angle here, so here's my angle, and I have a side, and I have this other side, well, it turns out that I could, by construction, actually create two sides of this length over here, and it would either give me this triangle or it would give me this triangle, but they both have the same parts. Like this would be congruent to that, and this would be congruent to that. So notice by angle, side, side, I could potentially, with those three pieces of information, come up with two completely different triangles. For that reason, ask does not work. Sorry, pardon my French. All right, however, we can tweak those given pieces of information just a little bit. And if I take that angle and I make it a right angle, then what happens is your angle side becomes what we call the hypotenuse leg theorem. So it's still three pieces of information. You have to have a right triangle, but then one of the legs and the hypotenuse has to be congruent to the corresponding leg and hypotenuse of another triangle, and then you have two congruent triangles. Basically, if you have two sides in a right triangle, the Pythagorean theorem sort of dictates that this third side would have to be congruent to the other triangle, and that's why this works. All right, so we see here in A, and this is important, it has to be a right triangle. So when you're doing proofs, you have to establish that you have a right triangle. Okay, so there's more to it than just then. In a right triangle, if the corresponding, if A corresponding, that's what I really should say. Sorry, I'm mess up. Hello, got to pull out the right tool. Hey, why is it not letting me erase that? I guess I have to go all the way back. Oh, this is kind of annoying. Sorry. I just want to make sure it gets down correctly. So, it's getting rid of everything. It's going all the way back. All right. So, hypotenuse leg. So, in a right triangle, if a corresponding leg and hypotenuse are congruent to the leg and hypotenuse in the other, in another triangle, then the two triangles are congruent. All right, and this one is called your HL theorem, hypotenuse leg. It is sort of, when asked, you will never, ever use SSS as a reason for two triangles being congruent. But what you want to look for is if there was a right triangle, then you say HL. All right, so let's take a look at how this works. So we are given that B is the midpoint of CD. And I'm going to kind of, let me see, did I give myself 1, 2, 3, 4, 5? All right, I guess, I'm going to, B is the midpoint of CD. I'm going to take more steps than I've given you things here because I'd like to do this in a logical way. So B is the midpoint of CD. So here is B. And they've given us that it is the midpoint of CD. So remember, what does that tell me? That's not a part of our triangle yet, but it does give me that I know BC is going to be congruent to BD. And the reason for that, because it's a midpoint. So you say definition of a midpoint. That's what a midpoint does. Break something into two equal parts. All right, so those two went together. Now I'm going to bring in that angle C and angle D are right angles. That was given to us. Now, that doesn't make for a right triangle. So what you have to say, because remember, HL only works in a right triangle, but you are now allowed to say that triangle ABC, oops, forgot the A, ABC, and triangle EBD are, in fact, right triangles. Why? Well, that's the definition of a right triangle. If you have a right angle, it's got to be definition of a right angle. I can't talk and write at the same time sometimes. Definition of a right triangle. A right triangle is a triangle that has a right angle. That should make sense. All right, so 3 and 4, those steps go together. And remember, okay, so let me do this first. Let's put down our last given, which was right here. They gave us that AB segment is congruent to segment EB, and that is already marked up on the triangle. So let's look at what we have here. We've got this part. This is BC and BD. That was right here. We have AB and EB, so one of those is a hypotenuse, one of those is a leg, and we do have a right triangle. There's that third part that you need, even though this is not actually a part when you're doing HL. You do have to have established. So that allows me, whoops, probably not nice to write the conclusion in highlighter. That gives me that triangle ABC is congruent to triangle EBD. And now, oh, I'm sorry, I never filled this in. That was given to us. So I put all the givens. Sometimes it's nice to break them up because they have logical consequences, and so to kind of chunk it together like that. And our reason here is going to be the HL theorem. All right, now not every time that you have a right triangle do you have to use HL, but it is quite common. So this last little bit, if we were in class, we would have you, again, go into your breakout rooms and determine. So what you might want to do is turn off the video for a second and see if you can, on your own, determine which of the following triangles could be proved congruent by side, 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 or hypotenuse leg. And then I'm just going to keep going. So in example A, I notice I have a shared side, and I see three congruent sides marked. So this one can be proved by the side, side, side theorem. In this next one, I do have a leg and a hypotenuse, so the HL theorem can be applied there. In number 3, I notice I have a shared side down the middle, and I have right triangles and a leg, so this one also can be shown by the HL theorem. Now when we come down here, notice there's nothing marked here. However, we do have this down the middle, so they're trying to trick you. This one is the side, side, side theorem, because we don't have the corresponding right angle in the other triangle. In E, we have vertical angles here, so that makes that a right angle. And we do have a leg and the hypotenuse, so that would be your HL theorem. And then this last one, it is up for grabs. You could say the side angle side theorem, because you have side and an angle. You could say the HL theorem, because you do have a leg and a hypotenuse in two right triangles. Or you could say the side, side, side theorem. All of those would be applicable. And notice, really, this was irrelevant, this little piece right there. Okay?